Today, I will be talking about the resistor and the potentiometer. The resistor, which I have here, reduces the electricity from one point to the other point. And you can think of this electricity as either the flow of current or as the voltage drop that the electricity experiences from this point to this point. And a potentiometer, which I have right here, adjusts the value of your resistance from 0 to whatever the maximum resistance value is stated on your potentiometer. On my potentiometer, the maximum value is 1000. So if I turn the dial all the way to the left, generally it'll be 0, and if I turn it all the way to the right, generally the resistance would have a value of 1000. And this resistance is based on this pin on the left and the middle pin. And if we use the right and middle pins instead, turning the knob all the way to the right would have a resistance value of 0, and turning it all the way to the left would hold a resistance value of 1000. And this reduction of electricity happens based on heat dissipation. For a resistor, the heat dissipation, which reduces the electricity, happens inside the blue part. And for a potentiometer, which I have here, generally happens within the potentiometer. But if you have the same type that I have here, the heat dissipation would happen at the back of the potentiometer. And this resistance value that we're measuring is called ohms. And this is how you spell it. And the symbol for ohms looks like this. And this is the symbol for ohms. And your resistance value is measured based on Ohm's law. And Ohm's law states that the voltage of your circuit is equal to the current of your circuit times the resistance of your circuit. So voltage is equal to current times resistance. And voltage is measured in volts. Current is measured in amps. And resistance, as we already talked about, is measured in ohms. And the symbol for amperage is just A. The symbol for volts is just V. Whenever we add a resistor to our circuit, Ohm's law applies. So say our resistor is 100 ohms, so R is equal to 100 ohms. And say this is our circuit here. So I have my 9-volt battery go from the positive terminal to the negative terminal. And our resistor here is, as we stated, 100 ohms. And let's say our voltage stays constant and our resistor also stays constant. If we want to find the current going through our circuit, using Ohm's law, we can deduce that 9 volts is equal to I times 100 ohms. And to reduce this, 9 over 100 is just equal to 0.09 amps. To demonstrate Ohm's law, I have my resistor here. And as it says on the multimeter, my resistor is about 100 ohms. And another way to tell if your resistor is 100 ohms is to look at the color bands of your resistor. And each band on the resistor would coordinate the resistance value that you would apply. So now that we've discussed the value of a resistor, I'm going to replace these two ends with the two ends of my DC power supply. Here right now I have it connected to my multimeter, and I will switch that out. And here is my resistor connected to my DC power supply. The LCD screen here indicates the voltage that I'm supplying my resistor with, and here indicates the amperage that I am supplying my resistor with. And if the voltage changes, the amperage must change too, according to Ohm's law. And right now, if it's 0 volts, it's going to be 0 amps, because if you have no current times whatever resistance value, you're going to have 0 volts. But if I turn my voltage up to 9 volts like we had in our example, our amperage should be 0.09 amps. And as you can see, my connection here, I'll turn it up. You can see my amperage changing, and as we hit 9 volts, it's a little bit over 9. My amperage is about 0.09 amps as to be expected. Now, one thing to note about resistors is that they have a power rating. And the equation for power that I will write down. And this power rating, which is measured in watts, specialized as W, is equal to voltage times the current. Or if you want to rewrite this, it also equals voltage squared over your resistance value. And that's in power. Power is denoted as P, measured in watts, and watts is spelled W-A-T-T-S. And this power rating is designated to whatever the manufacturer set it as. And the resistor that I used in my example is rated for 0.25 watts, or a quarter of a watt. If it exceeds that, what will happen is that the resistor will heat up, and that heat buildup will either cause a fire or cause the resistor to smoke up. I'll go ahead and show you what I mean. So for this example, I have switched my resistor from 100 ohms to 10 ohms. And the resistor's power rating for this one is half a watt. Whatever my voltage is and whatever my current is, multiply them together, and if it exceeds half a watt, this blue part is going to either cause some smoke or is going to cause a fire. Just a quick calculation before connecting it to the DC power supply. To test our power or wattage limits of a resistor, we're going to use V squared over R. And we know R is going to be 10 in our example. So R is equal to 10 ohms. And we know that the power in watts is going to be 0.5 watts. And to simplify the equation, we get V squared is equal to, or power, 0.5 watts times 10 ohms. Which, to simplify this, V squared is equal to 5. And simplifying this, our voltage limit is 2.236 volts. So here I have my 10 ohm resistor connected to my power supply, which is 0 volts right now. And I'm going to go ahead and turn my fume hood on. And now I'm going to turn the voltage up to 2 volts. So far the resistor is getting a little bit black. And if we turn it up a little bit further, so I have 5.7 volts. I can smell the smoke now, but it still looks like it's fine, but it's blackening out. Let's turn it up a little bit more to say like 9 volts. 8 volts should be fine actually. And yeah, you can see the resistor smoking up and turning on fire. And to shut down my power supply now. And yeah, you get this like a burnt of a crisp resistor. Keep in mind that you'll have to apply Ohm's law for each component. So if you have 2 resistors, you're going to have to apply Ohm's law for each resistor. And if you have multiple components in your circuit, it can be either set up as a series circuit, a parallel circuit, or it can be set up as both ways. So here I have 3 different circuit diagrams. This one here is a series circuit. And series circuits have their components in a straight line. For parallel circuits, there's a junction which is usually indicated by a dot, one here and one here. That would indicate that you're working with a parallel circuit. And you can think of these junctions as intersections that can allow electricity to go in one path and also the other path. And you can have a circuit that both has a series circuit and a parallel circuit. And to find the total resistance of a series circuit, the equation that you would be using is R1 plus R2 plus R3 and so on. And if you want to find the total resistance of a parallel circuit, you would use the equation R parallel equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. And if you're trying to calculate the total resistance that both has series and parallel components, you would have to find the total parallel resistance first, then add up with the series resistance to get your total resistance. So first step, find parallel resistance. Then you find the series resistance. And your R total would be the result of R parallel plus R series. So here on my diagram, you would find the resistance of these two resistors first. Then you would add this resistance here, which is in series, to whatever the parallel resistance is that you have for these two resistors here. And you just add these together for the total resistance. And I'll give an example to clarify what I mean. So here's my example here. I have a 9-volt battery, and these resistors are parallel because the junction here that splits the electricity into different paths, as I've said before. To find the total resistance, we'll need to find the parallel resistance first. And our parallel, as you recall, is equal to 1 over R1 plus 1 over R2. And we'll say 200 ohms is for R1 and 300 ohms is for R2. And that would equal to 1 over 200 plus 1 over 300. And that would equal to 120 ohms if you put this equation in the calculator. Then we add our parallel resistance of 120 ohms with 100 ohms that we have in series. And our total now is equal to 100 ohms plus 120 ohms, which equals to 220 ohms of the total resistance of our circuit. Now let's say we add a resistor right here. And let's say this resistor's value is X. Here for our series, instead of the total being 100 ohms, the total is now 100 ohms plus whatever this X value is. And our total changes by having our series, which is 100 plus X, plus the parallel resistance value, which we have as 120, to get a total of 220 plus X. Now, if we want to find the current through each component of our circuit, or if we want to find the voltage drop of a component, which is this point to this point here, this point to this point here, this point to this point here, and this point to this point here, we can find this by using 3 different sets of laws. And the voltage drop is basically the amount of voltage the component is taking throughout the whole circuit. The first one is what we've already talked about, is Ohm's law, which, as you recall, is voltage is equal to current times the resistance. And the other 2 sets of laws is called Kirchhoff laws. And Kirchhoff laws is spelled like this. And the 2 laws that Kirchhoff law state is that the sum of the current inside your parallel junctions is equal to the sum of the current that's going outside of your parallel junctions. So here is the junction for my parallel circuit and the current coming in from my 100 ohm resistor. So this would be my current going in is equal to the current going out of my 100 ohm resistor. So for now, in this example, let's not consider X as our resistor value. And here would be the current value going out of our parallel junction at this point here. And the other law is that the sum of the voltages, the sum of the voltage drops across the circuit is always going to be equal to 0. And voltage drop is always going to be negative. Here's the voltage from our DC power supply or from our battery. And for each component here that's experiencing a voltage drop, so we have 3 components. One of them is from our 100 ohm resistor, the other one is from our 200 ohms, The other one is for almost 300 ohms. If you add the voltage drops of these three, they should equal negative 9 volts. All these voltage drops would happen from the positive side of your battery or your power supply to the negative side of your battery or power supply, also known as ground. And here is my positive side and here is my negative side. For the Kirchhoff's current law, your components that are in series will always have the same current. And you can tell by assessing which components are before your first junction and which components are after your last junction. In this case, this is my first junction, this is my last junction. If there's any more dots, you only consider the first and the last dot. So whatever components I have after this dot, like this crossed out resistor I have here, or this 100 ohm resistor I have before my first junction, these two are series components. And after this first dot, or before this last dot, I'm going to have to consider those components as part of a parallel circuit. And the current that's being drawn from your power supply or your battery is determined by the components of your series circuit. So if my current that is passing through my 100 ohm resistor is 0.4 amps, the current that is being drawn from my battery or power source is also 0.4 amps. And if we want to find the current and the voltage drop going through each component, we can either start with the voltage drop equation or the current equation for our Kirchhoff's laws. If we were to start with the voltage drop equation or Kirchhoff's voltage equation, we could say that our 9 volts minus 100 times I, and keep in mind that 100 is our resistance and that our resistance times our current is our voltage based on Ohm's law, minus our next component, and these two parallel components as we solved earlier is 120 ohms. So here we're going to have 120 I. This is also the current going through our 100 ohm resistor. So this is I1, and adding this together will also be I1. So this would be minus 120 I1, and that, based on our equation here, would equal to 0. And if we solve for I1, we get 220 I1 is equal to 9 volts, and I1 would equal to 0.0409 amps. And that's going to be the current draw from our battery or our power supply. We already said that I1 is the current passing through our 100 ohm resistor. Let's say the current passing through our 200 ohm resistor is I2. And the current passing through our 300 ohm resistor is I3. Now, based off Kirchhoff's laws for current, the current going in, as we stated here, is equal to the current going out of our junctions. So another way to write this is that I1 is equal to I2 plus I3. We also know that the electricity, which you can call current now, runs through two paths. One of them runs through this path here, and one of them runs through this path right here. And based on this fact, we can write two equations to solve for the current and voltage drop passing through each component. The first equation, we'll go back to Kirchhoff's voltage law, is that we have 9 volts minus 100 I1, and keep in mind that's the voltage for this component here, minus 200 I2, and that's the voltage for this component here, is equal to 0. And the other equation, which we have this loop right here, we can go ahead and write as 9 volts minus 100 I1 minus 300 I3 is equal to 0. And to simplify these two equations so we can combine them together, another way to write these two equations is so now we got two sides of the same coin. We can write our final equation as And finally, we can cross these two terms out, just subtract 100i from each side, and we get two different results. We either get or. So the next step after finding what I2 and I3 is to go back to Kirchhoff's current law, which is that the current going in of a junction is equal to the current going out of a junction. And this equation, simplified, we get I1 is equal to I2 plus I3. And we determined that I3 is 200 over 300 of I2. So I'm going to replace I3 with this. Similarly, I can replace I2 with 300 over 200 I3. And now we have our term for I1 that we can replace with either one of these two equations. And I'm going to go ahead and use this equation first to replace my I1 term with my I2 terms. And if I wanted to use I3 for this equation instead of I2, I can also write down the following. Now we can figure out what the current is going through I2, which is right here, and our current going through I3, which is right here. And if I simplify the equations, then put it into the calculator for I2 and I3, I would get a current value of 0.0245 amps going through this component here. And the current going through this component, the value is going to be 0.01636 amps. And if we go back to our original current equation from our Kirchhoff laws, our simplified version is I1 is equal to I2 plus I3. If you plug it into the calculator, I1 is going to be 0.0409 amps. It's exactly the same from what we calculated right here. And as I said before, 0.0409 amps is going to be the current draw from the battery or from your power supply. And here's a quick clip of me soldering together the circuit that we've talked about using 6 100 ohm resistors, a PCB board, some solder wire, and a strand of red and black wire. And yeah, here is my completed circuit. This is my positive end of my DC power supply, and this is my ground. This here is my 100 ohm resistor. Here's my junction to go into my 200 ohms resistor. These are just 2 of the 100 ohms resistors in series. And here is just 3 of my 100 ohms resistors in series. And 200 ohms here is parallel with my 300 ohms right here. And this is my junction going out to ground right here. I have connected my finished circuit with my power supply right here. And right now it's at 0 volts, but when I turn it up all the way to 9 volts, you can see that the amperage is pretty close to what our results are, which is 0.0409 amps. And another thing to keep in mind is that do not connect your hot or live wire together with your ground lead. Otherwise, it'll cause a short circuit. And a short circuit basically causes an infinite amount of amps to go through a wire because there's no resistor. And to make your life easier, be sure to buy a DC power supply with overvoltage and overcurrent protection. Let's talk about the potentiometer now. A potentiometer is also called a voltage divider. A potentiometer basically adjusts the resistance to a value that you want. And this value can range from 0 to whatever the maximum rated resistance value is on your potentiometer. And for the potentiometer that I'm holding here, The maximum resistance value is 1000 ohms. As you can see on the potentiometer has 3 pins. For our 3 pins, let's call the leftmost pin pin 1, the middle pin pin 2, and the rightmost pin pin 3. Pin 1 is typically the voltage coming into your potentiometer, so we can call it V in. Pin 2 is typically your voltage that's coming out of your potentiometer, so we can call that V out. And just to clarify, this is the voltage difference between pin 2 and pin 1. And this is true with whatever component you place in parallel between pins 1 and 2. I'm going to go ahead and say parallel to pins 1 to 2 or pins 2 to 1. And pin 3 is typically your ground. The equation that you can write down to get your voltage value and your resistance value is the following. You have V out is equal to V in times R2 over R1 plus R2. And pins 1 to 2 represents the resistance value of R1. And pins 2 to 3 represents the resistance value R2. And your total maximum resistance, which for this potentiometer is 1000, R1 plus R2 is going to be 1000 ohms. So R1 plus R2 is equal to the maximum resistance. And just to make the voltage coming out a little bit clearer, from pin 2 to pin 1, also pin 1 to pin 2, they are the same thing. And if we put an LED parallel to pins 1 to 2, pin 1 being the positive side, pin 2 being the negative side, I have a potentiometer that does not include this LED that looks like this. So this is my positive side, this is my negative side, and if I connect it to my power supply, so turning my potentiometer to the right would reduce my R2 value and increase my R1 value. R1 plus R2 is still going to give you your maximum resistance value. So as I turn it to the right, my resistance decreases and my LED would then turn on. As you can see here, turning it down, turning it back up. If I were to place my LED in series with my resistor, I would have to put the positive lead of my LED to the second pin of my potentiometer and my negative side of my LED to ground. So instead, it would look like this. And since it's all the way to the right, it's going to have a maximum resistance of 1000 ohms. And if I turn it to the left, my resistance decreases and my LED gets brighter. And my resistance value will be close to 0 ohms. So from pins 1 to 2, my resistance value would pretty much be 0 ohms. And my resistance value from 2 to 3 is pretty much 1000 ohms. And if I turn it all the way to the right, pins 1 to 2 would have a resistance value of 1000, and pins 2 to 3 would have a resistance value of close to 0. And yeah, that'll be it for this video. I hope you found this video helpful, and yeah, thanks for watching.